So in this video we are going to see all the available commands in various tags. In the last video we have seen what are the mandatory commands, what are the optional commands, and the custom commands. And this is an example of the tag from NXP. This is SLI. This is the first generation of the ICODE tags. This is ICODE SLI, sorry. Now here, if you can see here, it says the supported commands. Now we have got the mandatory commands. We've got inventory. We know the inventory and stay quiet. These two were the mandatory commands in the standard. So these two are also present in this tag. The optional commands, we have seen the read single block. Now most of the optional commands which are mentioned here in the standard are present here. We got read single block, we got write single block, log block, read multiple blocks, and you got select, reset to ready, write AFI, lock AFI, so write DSFID, log thing, and all these commands that are mentioned in the standard are also present in this ICODE SLI. Let's see if it has got any custom commands. Look at that. It does have got some custom commands also. And remember, the documentation says in the custom command, the command carries the manufacturer code. Now here the documentation says, it has explained, it has mentioned here the manufacturer code for the NXP 04. So all custom commands will carry the number 04. And some of these commands are inventory read. You know, there is no command called inventory read in either mandatory or optional. So obviously this is a custom command. And bear in mind, all these custom commands are there to provide, to improve the speed, or to provide, to read more data than mentioned in the standard. Say, for example, inventory command here does, in addition to the inventory, can also read some more information to you. Okay, so all these custom commands are there to improve the performance of the tag. Here got inventory read, and once you are comfortable with the structure, this you can easily understand all these commands. Probably this is one of the best example to look at the optional data. So the flag here has mentioned, there's an option of AFI is present or something like that. And you got something called fast inventory. Again, as the name suggests, it is a kind of a fast way of getting the data from that tag. So likewise, every tag has got its own custom commands. Let's see some of the commands available in M24LR04. And here, this, I'm not going to read this out because it's very obvious from here. So this has got the mandatory and most of the optional commands up to here. So followed by, it has got many custom commands: initiate, inventory initiate, write sector password, lock sector, and so on and so forth. Now it has got probably more custom commands than the ICODE SLI. So it all depends on the structure of this tag. Probably this has got more memory, or this has got the more like you can see here, it has got something to read the configuration, write the configuration, and so on and so forth. And I'm also going to see what is available in the Texas Instrument tags, the TA tag. Here this is cleanly laid out. So you can see you got the mandatory commands, followed by the optional commands, followed by, it has got just two the TA custom command, write 2 blocks and lock 2 blocks. And also there's more information here. Say for example, take this read single block as an example. So this, it says it can be used in the address mode, non-address mode, select mode. This can also work with AFI. again you have to read the documentation. Once your fundamentals are clear about all these commands, you just have to probably additional some extra features will be added when inventory is set or the flags are set. I would like to make this video little bit interesting, by coming out of the theory now. As you can see here, I've connected my CR95HF board. And if you remember, I also have got the OmniKey reader writer, but however, I could not find any kind of like a free software to show or to demonstrate this the tag I'm going to show now. Now this tag, this board, it comes with the M24LR EEPROM as well, but I'm going to use the ICODE SLI. So I'm still not very sure whether you can use this in full, but so before you do that, if you go to this ISO15693 section, you can see, for example, if you go to this M24LR, all the commands that are supported by that board are available here. So this is a nice tool to play with, and also if you are creating your own software, this tool is so important that it shows you all the commands you're going to use in your program. Now I'll be using this in the later videos. So somehow you can see here, you can write the DSF ID, you can write the AFI and lock it, and you can also write the sector password or log the sector password and present sector password. So all these buttons have got, they corresponds to a command in that board. Now I'm not going to use this one at this stage though, because this is this board is it has got so many features, and it takes a separate video. Now I'm going to choose the LRI 1K. Now this is a little bit simpler. Now let us try to do some operation without going through the commands. Now let's try to make out, but we have seen the commands now. Let's try to make out and try to use the commands. So the very first thing is the inventory command. We know the inventory command is the first thing you do. It builds up the inventory of all the tags, and if I hit this inventory, you can see that there is sequence of command going here. So it is 260100. So if I think it's not, you can't forget, sorry, now all these things are part of the command. The 26 is the flag, 01 is the command, and 00 is also a part of the command parameter. So I will come back to this soon. Now you got some output, and this output is nothing but the UID of this tag. Now let's try to get the system information. We have seen get system info is part of the optional commands, and the documentation says this should give you the size of the memory and other information. If you click that, you can see now there's a command going here, 02 followed by 2b. Just if you go back to that and see the system get system information, the command is 2b, but keep in mind every request command starts with the flag. The very first byte is the flag, so followed by the command itself. Now here 02 is the flag followed by 2b, and in this software you will never able to see the CRC. They are all handled by the within the board itself. So you got all this information, and this information decoded here. It says the UID of this is all the information we get from the get system info command. It says the DFID is 0, that's the default value, 0. AFI is also 0. 00 means is not set. The block number, I think this is the number of blocks. So this is probably it's 16 plus 11, 27. So there are, the maximum block number is 27, and the block size is 3, and the IC reference is 01. Now this is not the manufacturer, this is the it's a type of the tag. Now the documentation explains how to interpret all these bytes. Next I'm going to show you a little bit of a reading. We often use these tags for reading and writing. So I'm going to use this read single block command. I'm going to read from 00 to 00, just one single block read. So you can see that looks like this is a very familiar numbers. Looks like this ICODE tag, SLI tag, comes with a NDEF, an empty, the NDEF NFC data already written there. So E1 I'm familiar that E1 starts with the E1 is the first byte of any NFC formatted tag. Now let's try to see from 03. Sorry, no, single, yeah, somehow it worked here. I thought the read single block reads only one, and keep in mind this is the software that doesn't belong to the ICODE SLI. This is belong to a chip from ST LR1K. So I'm not expecting 100% output from this software. So you can read, probably now you can read the multiple blocks. So read from the entire, say, from 100 to 10. Read multiple, yeah, read multiple works as well. We are reading everything, and it looks like here it's getting truncated because of the width of the screen. So you can still see there's some data coming out of here. Okay, now can we write? So I'm going to write something to, say, block 1. If you click on write single block command, I'm going to write, say, 41, 42, 43 and 44, and give single write block. And if you just have to, oh sorry, what has happened here is the write command has written everything probably from 00 to 10. If you look at the commands here, there's so many write single command has gone. So this is how software works. Now there is some error here. Let's not worry about that. I'm going to read this and see what happens. Look at that, the same data has been written for all these blocks. So we have seen how to write, how to read, and if you want to say I want to change the DSF ID, so I'm just not very sure. Okay, let's put write DSF ID. Yeah, you got something here. Now if you go back to the documentation, probably now the families of AFI. So let's have a look at and give some sensible values for that as well. Yeah, over here. Now we know that the higher nibble with 1 for transport cards, and 2 for financial, 3 for identification, and 5 for medical. I'm going to use 50. So I want the DF, sorry I was wrong. Just give a cancel. Let's try the AFI. It's not DSF ID, sorry for that. So write, I'm going to put 50 and say write AFI. Now the write AFI command, you can see it says 0 to 27 and 50 is what our data is. You got some response here. Now how do I check the write? Is there any command to read the AFI? There isn't any. However, we know the system information can give us the AFI. So get system information, look at that, we are able to write AFI. So let's try to change DSF ID. Write DSF ID. I'm not very sure whether this is something a software developer or the creator of the software can decide. So I'm going to put 1.5, right, go to inventory and give the get system info, right, successful. I don't want to try locking because I'll be using this tag in my future demo as well. Now the other commands like write kill, lock kill, they're all part of this LR14K, LR1K. And in here, we discussed about this. We saw the flag can indicate whether it's a low data rate or high data rate, or whether to use the 10% modulation, 100 modulation. So all those things can be, if you want a fast data rate, you can tick here. So you have to see the actual documentation of this ICODE SLI, whether the fast data rate and all these things works or not. I'm going to try this lock blocking status. We have seen this is part of the I'm not going to block, sorry, just get this one. So get multiple block security status. Now here, along with each block, you get the value of the security, which is only 1 bit. We have seen in the documentation that says whether it's locked or not locked. And I think the value of this 1 byte also depends on the tag. But the standard says it's just, sorry, I was wrong. I think the security state is completely dependent on the tag, so nothing to do with the the standard. Next, I'm going to quickly go through various commands, and we are going to come back to these commands when I actually show the working of these commands using a software. Now the very first command is the inventory command. The command code is 01, and these are the things you can send in the request frame. So the flag, remember, in the flag, the inventory flag must be set to 1. So, and followed by this inventory command, you can send a optional AFI. So the AFI is meant for selecting those tags which satisfy the AFI. So say for example, you got assume that you got around say 5-6 tags near the VCD, and this, the first tag is a Medico tag with 50 AFI, and this is maybe transport with 10, and this could be something else. Okay, if the inventory command carries the information of AFI as 50, only the first 2 tags will be selected for the inventory. So the value for the mask length and the mask value is very specific to the anti-collision method used in this standard, which I'm going to cover in later videos. So that's very simple inventory command. Now the response to the inventory command is you get the DSFID and the UID. So you'll end up getting the 1 byte of flag, 1 byte of that, and you get 8 bytes of UID followed by 2 bytes of CRC and EOF. Now we have seen the output of this inventory command, but we are going to go through that detail in the next videos. See, some of the commands will not give any response. Stay quiet is one of them. So as the documentation says here, this command, there will be no response for the stay quiet command. Now also mentions, okay, what is the meaning of the quiet state. So this says if a WIC is in the quiet state, the WIC shall not process any request where the inventory flag is set to 1. Now this is a method used to select the tags in the inventory process, and the WIC shall process any addressed request. So when the tag is in a quiet state, you must use the address request. So address request means the request will carry the UID of the tag. You are addressing a specific UID. Now it also mentions about how to come out of the quiet state. Either you reset the power or you issue a select request, or you can forcibly make it go to the ready state. Remember, the ready state is the state a tag reaches as soon as it enters the magnetic field of the VCD. So that is done by there must be a command for reset to ready request as well. So this is the format of the stay quiet. So in order to use, there is no optional fields here. In order to use this stay quiet request, you must send the stay quiet command and the UID and the flag, okay, as well. So the documentation mentions here what's the requested parameter, and it says the UID is a mandatory. Now, obviously the flag and the commands are always mandatory, and whether the bit inside here was optional, but the document says UID is a mandatory field. And also it says the select flag is set to 0 when address flag is set to 1. So that's what you have to do. So keep in mind, whenever you are addressing a specific UID, you must have the address flag in the flag section to 1, and you must have the select flag set to 0. The read single block with the command 20, and also it says, so you can, the WIC will read the requested block and send the value back to you. If the option flag is set in the request, the WIC shall return the security status of the block as well. So this is the use of the option flag. Remember, we have seen this option flag in the set of flags. So if you don't set this, you just get 4 bytes of data. If you set this, you'll get 4 plus 1 byte of security value. Here what you see, the grayed out portion here means optional. So you can send this request without a UID, or you can send a request to a specific UID, that's the address mode. In that case, it will have a UID of 64 bits here, and it says the UID is optional, but the block number is obviously, to read a block you must specify the block number. So here, if there's any error reading, assume that you try to read, give a block number more than what is there in the tag, the error flag will set to 1 and you'll have error code here. So if there's no error, you'll end up getting the data. If you requested the optional flag, the first byte is the optional bits, and followed by the data. Again here, the data length depends on the tag. Some tags are 4 bytes, 32 bits, some are 64 bits, or some could be can go up to 256 bits, 32 bytes of depends on the tag. So again, you can see here the explanations are so simple. So it's very easy to understand all these commands, but you have to practice to master these commands. So write block, the command is 21, and here you have to specify the block address. You can directly go into this and understand rather than reading here. And there is something else as well, okay, you can also specify whether you want 100% modulation or not. So here you can, now whenever you see this UID with a grayed out, it means you can send this command in the address mode, where the address flag in the flag will be set to 1. Now here, if the write is successful, you will get the flag. That's all. There is no data here. The flag will be set to 0. Otherwise, if there's an error, probably when do you get an error in the write block? Probably you're trying to write to a locked block, or you're trying to write to a block that is password protected, or you're trying to write to a block, which is not existing at all. Lock block here. So this is used to lock the block from writing. This is basically trying to make the block read only. And there's something else, I just have to. There's something important here, during the write operation and when the optional flag is set. Usually what we expect is when the VCD sends a command, maybe after some time when the command is processed, the WIC will return the response. So this is the general, the request and response structure. However, I'm still not very sure, why this is it is here. So when the option flag is set, it says the WIC shall return the response when it has completed the write operation. Sorry, when it is not set, the WIC will immediately return the response. So that's fine. This is just a normal operation. However, when the WIC is set, when the flag is set, the WIC will respond only after it receives a end of frame command from the VCD. So here, probably the WIC, the tag, will return the response only after a request coming from the VCD. And this request, is like empty request which has got no command, no flags, just a single byte of EOF. Now you have to keep in mind, everywhere this is this mentioned when the option flag is 1. Say for example, in the lock block also it says when the option flag is not set, the WIC will respond after it has done the processing. When the option flag is set, the WIC shall wait for the reception of the EOF. I think that's one of the reason why I did not understood before what is the purpose of this button, a send EOF. Let's try to see what the structure of this send EOF. Now it is, if you can see here, there's nothing here literally. So it says 01 and 0400. So not very sure. This I think is an empty command. So for locking the block, you have to specify the block number and the lock bits. The lock bits here, the documentation says it's just a byte. So just in the byte, just the last bit is used to indicate whether it's a lock or unlock. I think you cannot use unlock. Once the lock is done, it's locked forever. And all the remaining bytes, probably is like a don't care or the value zeros. You can target this command to a very specific tag by setting by using address mode. By address flag is 1 and UID is 64-bit. And the outcome is the same whether you get error or a success. The next is read multiple blocks. Here, as the name says, you're going to read more than one block. Again here, the option flag is set means the WIC will also return the block security status, which we have seen in the demo. And the blocks are numbered from 00 to FF. So the maximum block number is 0 to 55. And the question is what to do if a tag has got more memory. Probably the manufacturer would introduce a custom command to read more memory. So here the command structure is very obvious. You give the first block number and the number of blocks. But however, there is a bit of a catch here. The number of blocks, if the value is 6 and you read the 7 blocks. So you just have to keep in mind the way these commands are executed. If the value is 0 0 means you get single block, and again here you can use the address mode or non-address mode. So if it is successful, you'll end up getting the 8 bits followed by the data, and this whole thing repeats for the number of blocks you are requesting. So you get a block status byte followed by the block length. So assume the block length is 4 bytes, you get 1 byte of security value and 4 bytes of data, and 1 more byte of security value, 4 bytes of data, and so on. The write multiple blocks, here as the name says, you can specify the block, starting block number of blocks, and give all the data. It says here the block length 32 bytes, it repeats so many number of times. And here also the option flag behaves, if it's set, you have to request with the EOIF in order to get the response from the VCD. I'm still not very sure on what occasion you will use this sending EOIF. The select command, so if you want to bring this tag into the selected state, you can use the select command. Again, if there is already a tag, assume that there are multiple tags in the inventory or in front of the VCD. If you select a different tag, the tag that is already selected will get deselected, probably returned to the ready state. Now here the UID is mandatory, so the select command is always a addressed command. So even the response is very obvious here, whether you get error or no error. The reset to ready, so here you're forcibly taking the tag to the ready state, and this can be either addressed or a non-addressed. So again the responses are very obvious from here. The write AFI command is the 27. We have already written an AFI, and here also this is a write operation. This changes the AFI. Now again the option flag behaves in very similar in what it was in the write block command. So you get a response only after sending EOIF. If you don't use the option flag, you get the response. It's not immediately, it is some time, and maybe this is the time the tag takes to process the write command, and you might get error, and there are some occasions where the write could be unsuccessful. For example, if I'm not very sure whether you can find a tag without an AFI. Probably if the AFI is locked, okay, you cannot write it. If the AFI writing is password protected, it's quite possible you cannot write it. So in all these occasions you get error. The lock AFI, again you are just setting making the AFI. Once you set, probably all these features are required during personalizing the tag. You write the lock, and then you write the AFI and set the lock bit so that the AFI becomes read-only. So there are very few concepts we have seen here which repeats for every command. So write DSFID, so you can change the value, and this is probably an application value. You can write whatever you like. So if you have got 10 different types of tag in your system, probably you can identify what is the structure of the data. It could, for example, if the DSFID is 01, you can that could indicate the tag as a NDEF record. If it is 02, it could mean the tag as just a raw data, and so on. So again here it's all the same concept here. This can be addressed or non-addressed, and you have to pass the new DSFID, and this is the command. And locking, you can lock the DSF ID once written and make it read only, and get the system information. So if you have seen this command, when you send this command, you get all this information. You get the UID, you get the DSF ID, you get AFI and other fields. So the other fields depends on the tag. You have to see that the tag data sheet to understand the other fields. So this is the structure of the flags here. This is one of the examples you are seeing for first time. The flags in the response. So far you have seen it's only, sorry, it's not the flag, sorry, I was wrong. It's the info flags in the response. So this is a 8-bit value. If the first bit is 1, it says the DSF ID is supported by the tag and it is present. Similarly, AFI is supported by the tag. If it is 0, it means the AFI is not supported by the tag. So in that occasion, the write to AFI or read AFI or lock AFI might fail. So this will return you the memory size. The next bit, it says the memory size is supported and it is present. And this is the IC type. This is not the manufacturer's IC type. And we saw 01 is for ICODE SLI. And I think that the other information here probably it relates to the memory size. It says the block size in bytes and number of blocks. And we have seen this command, get multiple block security status. You can read the security status of say 10 blocks. So here you can give the starting block number and number of blocks, and the response will be the 8 bits of status, and this repeats for number of blocks you requested. The custom command structure, and all the custom commands will have the same structure. We'll have the flag, we'll have the custom bits, the manufacturer. It's a custom command actually. This is the manufacturer code and the parameters, and all these custom commands you have to refer to the tag datasheet. The next is the proprietary command, which is not mentioned here, and we're almost done with this document. If you go to the annex A, I mentioned before, so there is a pseudo code for anti-collision. So if you are writing an application, you just have to translate this algorithm to a program, and I'm going to now go through this in my future videos. And there's also a nice algorithm to compute the CRC value, and this is based on this is a standard here. I've used this, I've converted this, in fact there's no conversion required. This is written in a C, but most of my programs are in VB.NET or C#, so I'll end up converting this algorithm to the C# or VB.NET programs. And it's also, there's nice examples here. Once you write the program, you can verify, and in fact this tool already has got a screen. Now you can use this screen to verify your program. So you can use, look at that, ISO15693. So you can calculate the CRC. Likewise, you got CRCA, probably this is used in the MeFair tags, and CRCB probably the ISO15693 type B tags are used here. And then that's all. In the next videos I'll be showing you, we'll be going through these commands and we'll understand this and see how they work on the actual tag.